All right, basic units of measurement. Last class we left off, we were talking about scientific notation. So we talked about how to get into scientific notation. We didn't actually talk about how to get out of scientific notation, but you just reverse the steps. So you would just move your decimal place, but in the opposite direction. So if it's a negative, you would move the decimal, to the left. If it's a positive, you would move the decimal to the right, because a positive exponent means a big number. A negative exponent means a small number. Units are very important, especially in chemistry. They're important pretty much all the time. A lot of the time, though, if you don't include units, typically we kind of know what the units are contextually. So for example, in this sentence, when my son was 7, he walked 3. When he was 4, he could throw his baseball 8 and tell us that his school was 5 away. Your brain probably put numbers to all of those units. You probably interpreted this as maybe 7 months. He walked 3 feet. When he was 4, maybe years old, he could throw his baseball 8, maybe feet, and tell us that his school was 5 minutes, miles away. We didn't include units, so those aren't necessarily the units. This could be when my son was 7 years old, he walked 3 miles. Maybe it was like a walk jog, fundraiser at school. And when he was 4 decades old, he could throw his baseball 8 yards. Maybe he was just never really good at throwing a baseball, kind of like me. And tell us that his school was 5 kilometers, hours, feet away. So units make a big difference. We always want to make sure that we're writing our units. Never write a number by itself. Always write the units that go with it. This is a little bit annoying if you're not used to it. It was annoying for me when I wasn't used to it. Now that I'm used to it, it's not that big of a deal. Usually it doesn't add that much extra time. It's not that much extra ink. It's not that much extra graphite. But it will really help us out when we start doing unit conversions. When we're getting rid of units and bringing new units in, it makes a big difference. So always write your units. You will generally have units, so it's important that you write your units. An example of how another instructor teaches this. Who would like 5? Raise your hand if you'd like 5. Only one person wants 5? Minus 5 points. Who would like 10? Nobody wants $10? Okay, I'll keep them to myself. How about 100? Anyone want 100? 100 push-ups, thank you. Right, so including the units is important because you don't know what I was offering you because I didn't include the units. I was making them up after. So there's 2 unit systems. There's the one we're familiar with, sometimes called English system, sometimes called customary, sometimes called imperial. I think there's very slight differences between those, but for our intents and purposes, they're the same. These are the ones that we use, and also like London, Britain uses, whatever they're called. There's also the metric system, and that's what everyone else uses. Basically everyone else uses, and lots of people in the US also use, and that's the one that we typically use in science, the metric system. So the International System of Units, or SI units, the SI is in that order. It's not IS units because of the French that you can see here, and I'm not going to attempt. So system first, then international, and then this whole bit about units. So we use SI units, the metric system basically. And we've got a couple of our base units of measurement listed here. We won't cover all of these in the class. So for example, we're not going to talk about amps or candelas to talk about electric current or luminous intensity, brightness. However, we will talk about length, mass, temperature, time, and amount of substance, and our base units for those are shown here. We're going to go into a little bit about where those units come from. So one of the advantages also of the international system is that our base units, our standard units, are all based on constants. universal constants, things that will never change, which is great because then if somebody needs to access, hey, what is this exact unit? What is the length? We don't have to like go into the back room and pull out our holy ruler and say, this is our 1 meter stick. And then over time, after people have used that 1 meter stick so many times, it starts to wear in from the ends, and now our meter has changed, and all of our measurement systems go haywire. So one of our base units is the meter. It's slightly longer than a yard. It's about 3.3 feet. That's like, if you just needed to estimate, 3.3 feet would be a good number to use. It was defined in 1983, as the distance that light travels in a vacuum in 299,792,458th of a second. I think I said that wrong. The speed of light is just that number of meters per second. And it's always that number of meters per second as long as it's light and as long as it's in a vacuum. That speed changes if it's not in a vacuum. So if we can get a good vacuum and we can measure how long it takes for the light to travel, we can figure out a length based on that, and then we can make all of our rulers and stuff to spec. Our base unit for the kilogram used to be based on what you see in the picture here. It's not the glass bells, it's the little piece of metal inside. So the kilogram is slightly larger than 2 pounds. I think it's about 2.2 pounds. The international prototype of the kilogram defined the SI unit of mass until May of 2019. It's about 39 millimeters diameter and height, so about 1.5 inches, relatively small. It was 90% platinum and 10% iridium. So if you wanted to own a copy of the kilogram, platinum very expensive, iridium also expensive. Alloying them together, I imagine, takes a lot of skill. The problem with basing it off of this, they use this particular blend because it doesn't lose mass very much. A secret about the world is that everything is turning into vapor. Everything's turning into gas, including you. Just most of it's turning into a gas at a very slow rate, including metals. So like you can smell metals sometimes. There's little bits of metal coming off. There's probably some other stuff going on. So this tiny little cylinder in here is subject to just randomly ejecting little particles of platinum or iridium from its surface, even just sitting out at normal room temperature. And so they put this little bell on top of it to protect it, to keep all of that in, hopefully, and also to keep dust from landing on it. Because if you get dust that lands on your kilogram, well, now your kilogram weighs a little bit more, and the kilogram for the rest of the world, in theory, would change because of that, which is not great. And then because that one bell wasn't enough, they put another bell on top of it to protect the first bell. And that's all on its own special little platform. I don't know why it's on the little platform. And then they put a big bell on top of that, and it's on a glass plate that I assume is perfectly flat. So you get a nice vacuum-tight seal between the glass bell and the plate. And then they put an adapter on the top so that they could pull a vacuum so that there's no dust inside, and probably some other reasons. So they go through great pains to ensure that their kilogram doesn't change, but it's going to change regardless of what they do. And fortunately, in 2019, we got good enough at other things to get a new version of the kilogram. So the kilogram is now based on the universal constant, the Planck constant, which I don't think we talk about in this class other than on this slide. And so they use this absolute contraction of a machine, this monstrosity. I'm pretty sure if you put a human here, they would be about that tall, the little red thing. This is a very large machine. It's called a kibble balance, and the National Institute of Standards and whatever T stands for, that's where the NIST 4 comes from. They're the people that take care of our units in the United States. The NIST 4 kibble balance has measured the Planck constant to within 34 parts per billion, or this much percent error. So we will probably never measure anything to that tight of a percentage error in our lives. We probably won't ever see anything measured to that tight a percentage in our lives. But that's pretty freaking cool. I think that's really neat, and this thing just looks like an absolute masterpiece. So that's now how they measure the kilogram. It's based off of that instrument, which is pretty neat, which is based off the Planck constant. So that's cool. The kilogram is a measure of mass, which is different from weight. So mass is not the same as weight. However, we can convert between the two. We're making an assumption when we do that. So mass measures the quantity of matter, how much stuff is in an object. Would be a real crude way of putting it. How many particles are in a thing? Like, what's the total combined amount of matter that's in there? Weight depends on gravity. So weight is a measure of, I think it's force. Weight would be in pounds. Kilograms would be a unit of mass. So you may know that the moon has a lower gravitational pull than the Earth. I'll exaggerate a little bit. Let's say I weigh about 180 pounds on Earth. That might be accurate to me currently. So I weigh 180 pounds on Earth. If I go to the moon, if I'm remembering correctly, it's about 1/6 of the Earth's gravity. So I would weigh 30 pounds on the moon, on Luna. That's a really good weight loss program, but incredibly expensive. I'm not a billionaire, so I can't afford to do that. If I was to measure my mass in kilograms, let's say that I'm about 70 kilograms on Earth, just doing some real rough conversion. If I went to the moon, unfortunately, it's a good weight loss program, but it's not a good mass loss program. I would still be 70 kilograms on the moon. So the assumption that we're making when we're converting between kilograms and pounds is that we're on Earth, which is usually true. We're usually on Earth. Humans tend to be on Earth. So that's a little pedantic difference. The gram is another common unit of mass that we will see. We're often going to be measuring things in the lab in grams because they're smaller than kilograms. A nickel has a mass of about 5 grams. So 5 cents, 5 grams. 1,000 grams is 10 to the third grams is 1 kilogram. We'll learn about metric prefixes in a bit. Another of our base units is the second. Fortunately for us, it's the same second that we use, so we don't have to learn a new unit for time. And the second is defined using an atomic clock. So they take a bunch of fancy physics and engineering, and they get some cesium-133. We'll learn about isotopes later, but this is a very particular version of cesium, which we can find on our periodic table. And they count how long does it take for 9 billion and some change releases of radiation from a sample of cesium-133. And that's 1 second, this many periods. So when I was smaller, it was a little bit more rare. Like, I didn't have a phone when I was a child. Most of us probably didn't. We weren't born with our phones. So it was like better thing to talk about. How many of you have worn a mechanical watch? When you wear a mechanical watch and you've got other devices in your house, after a certain amount of time, you may notice, hey, my watch is out of sync with the oven, with the microwave, with the clock that I have in my bedroom, right? That's going to happen basically regardless of what you use to keep time, and you'll have to adjust one of them. How do you know which one's right? You wouldn't necessarily know which one is right, and so what would you do? You'd pull out your phone. My phone's out of arm's reach. You'd pull out your phone and you'd look at, okay, what is the time? The time on your phone is referencing back to an atomic clock that's keeping track of time all over the world. So this gives us a universal reference for how long 1 second is, and then somebody somewhere is keeping track of the official time for the world, plus or minus time zones. So that's cool. And this is a picture of an atomic clock. So they look kind of funky. When I was little, you could get devices that would like update their time with an atomic clock, probably by radio waves. With all of our SI units, we are going to be learning about what's called prefix multipliers. So the SI system uses prefix multipliers. Prefixes come at the start of a word or before a word. as opposed to suffixes that come after the word. So the SI system uses prefix multipliers, and these change the value of the units by powers of 10, which is really nice, because when you change by a power of 10, you just shift your decimal place over, so that can make unit conversions really easy. And since they all use the same prefix multipliers, you don't have to memorize a bunch of unrelated conversion factors. So when we're using prefix multipliers, we often want to choose a prefix multiplier that's convenient for a particular measurement. We typically want to pick a unit that gives us a reasonably sized number. What is a reasonably sized number? I would say that this is probably anything between 0.1 to 1,000, something that we can wrap our minds around. Once we start to get close to 1,000, I'm not sure exactly what 1,000 of anything looks like, but if we get to 1,000,000 or 1,000,000,000, I definitely don't know what that looks like. I can't wrap my mind around what those numbers feel like. Something between 0.1 to 1,000 will give us something that's like, okay, I can imagine what fraction of 1 would look like, or what 1, 10, 100 might look like. Here is some of the prefix multipliers. You will not be expected to know all of these, and this has some extra information on it as well. So the important things that we're looking at here, firstly, the prefixes, and then the other thing that you might look at is the decimal or the power of 10, where 1 in the middle here is our reference. Or our base. So like 1 meter would sit there. And then we've got units that are 10 meters per 1 unit, decameters, hectometers are 100. Deca and hecto are generally not important in this class, so I would say don't bother learning them. And then we've got kilo, so like kilometers, how we would measure distance if we were using the SI system for long distances. And then mega, giga, tera, peta, and those numbers, those prefix multipliers continue to go up. So kilo, if you see kilo in front of a unit, let's use blue. If you see kilo in front of a unit, you can turn that kilo into 10 to the 3. So on the previous slide, there's an example of this. All right, so 1 kilometer, the kilo prefix means 10 to the 3. So you can take 1 kilometer and sub in 10 to the 3, which equals 1,000. And when we turn this kilo into a number, then this becomes 1 times 1,000, so 1,000 meters. So 1 kilometer equals 1,000 meters. That's one of the ways that we can use prefix multipliers. Kilo is an important one to know. And then the others that I would say are important that you should definitely memorize would be centi, like centimeters, and milli, like millimeters. There's other smaller ones like micro and nano and pico that we might see come up in the class. We shouldn't see femto. I don't think I put femto on anything. And they go smaller than that too. All of us have probably encountered prefix multipliers at some point. When you get a new phone, when you get a computer, if you're asking your friend, hey, do you have a flash drive that I can borrow to transfer my file so I can go print it in the Student Success Center for free up to 10 pages a day or whatever it is? Right? The size of the storage that you have on your thumb drive, on your computer, on your iPad, on your phone, are measured in numbers of bytes, and usually they have megabytes, gigabytes, terabytes. These are using the same metric prefixes for mega, giga, tera. So if you have some familiarity with storage sizes, megabytes, gigabytes, terabytes, maybe even kilobytes, then you probably already have some sense of the scale of these units. And the nice thing is that once you get outside of this center bit, once you get outside of milli and kilo, they all jump by units of 3. So 10 to the minus 3 for milli. And then we go down 1 unit to micro, or 1 prefix to micro, and it's 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. So as long as you've got the kind of sandwich in the middle from kilo, you've got centi, you've got milli. When you go above that or when you go below that by 1 step, you're adding a power of 3. You're adding 3 to your exponent. That's how my brain remembers them. Just what's the order of the words, and then adding 3 for each one that I go up or each one that I go down. So these 3, kilo, centi, milli, these are ones that you should definitely memorize. Any questions about prefix multipliers? It will be a little bit confusing at first if you're not used to using prefix multipliers, but once you get the hang of it, it'll be a lot easier than like the units that we're used to. Because the units that we're used to have fun conversions, right? How many inches are in a foot? 12 inches in a foot. How many feet are in a yard? 3. How many feet are in a mile? 5,280? Do those apply to anything else? So like how many cups are in a pint? Is it 12? Is it 3? Is it 5,280? It's 2. How many cups are in a quart? 4. How many quarts are in a gallon? 4 gallons in a gallon, or 4 quarts in a gallon. How many teaspoons are in a cup? How many tablespoons are in a cup? So the nice thing about this is we don't have to memorize all of these. There's 6, there's 3, there's 4, there's 5,280, there's 12, there's 36. We don't have to do any of that because it's all using the same prefix multipliers. So as long as we're moving within prefix multipliers, it's always, we're just changing the prefix part. We don't have to worry about weird conversions with our units. There will be weird conversions with units. So if you were hoping for that, congratulations. There will be some weird ones. All right, let's see if we can pick a properly sized unit. So when we're picking units, if we've got it in scientific notation, we would want to pick the power of 10 that's close to whatever our scientific notation exponent is. So for example, what is the most convenient unit, or what is a convenient unit to express the dimensions of a mitochondria, the powerhouse of the cell, which is about 7.5 times 10 to the minus 7 meters in diameter. So we want to pick the letter that gets us close to 10 to the minus 7. So which of these units has a power of 10 that's close to 10 to the minus 7? There's 2 good options. Yeah, micro and nano. And micro's got this very fun, great, I can't remember the name of it. But it's a Greek letter. It's a lowercase Greek letter. So those are both about 10 to the minus 7. So micro, mu, that's what it is. Like the sound a kitten makes. That's 10 to the minus 6. Nano is 10 to the minus 9. So if we pick one of these units, that will get us kind of in the ballpark of the dimensions of the mitochondria, the powerhouse of the cell. And so we'll get something that looks kind of nice. So for example, for microns, which is another name for micrometers, it would be 0.75 micrometers, which is reasonably sized. If I asked you what's the size of 0.75 feet, you'd be able to give a rough approximation of 0.75 feet. If we put it in nanometers, it would be 750 nanometers, again in that kind of 0.1 to 1,000 range. What we wouldn't want to do is put it into megameters, because that would make it really, really small. I actually don't know what that would be off the top of my head, but it would be really small. Another thing that I'd like to point out here, if we look at A and B, our first two options, one of them is a capital M, the other one's a lowercase m. Those are for different prefixes. The capital M is for mega, the lowercase m is for milli. There are other such instances where capitalization is very important. If you use the capital when you meant to use the lowercase, that could throw you off on calculations. So capitalization is very important. Or case is important, upper or lower. Questions about our very fun prefix multipliers and base units? Great. There are also derived units. We know of some derived units. Derived units are from or formed from other units. They come from other units. That's what derived means, or it comes from something else. Many of our units of volume are derived units. So any unit of length, which is one dimension, like meters or feet, if you cube it, if you raise it to the power of 3, becomes a unit of volume. So cubic meters, meters to the third power, cubic centimeters, centimeters to the third power. These are also called cc's. And cubic millimeters would all be units of volume. So those are examples of derived units. Any measurement of area would also be a derived unit. So like square feet, if you're asking somebody about the size of the house that they hope to own someday, or if you're looking at the crazy houses that people show on Zillow, those would typically be square feet measurements that you would see. How much usable, livable space do you have? Those would also be derived units. Liters and milliliters are volume units that are not derived units. And there's 3.765? 3.785? I don't remember off the top of my head. They're similar in terms of liters and quarts. It's about 3.7 liters in a gallon versus 4 quarts in a gallon, just to give you some frame of reference for like the size of the unit. We're probably familiar with liters vaguely because you buy a 2 liter of Coke or whatever drink you like. That's typically the size of the package that you would buy if you're buying a big bottle. This is I believe it's a 1 meter by 1 meter by 1 meter cube with a 5'10" woman sitting inside. It's my mom. She went to some museum and they had a box that you could sit in. All right. Now on to what may be the thorn in your side for the rest of the class, at least in lab. Significant figures. So when we write out units, it's important that we write out the correct number of numbers. I think I said when we write in units. Nickels are an object that comes in whole numbers. Discrete, countable numbers. If we count 5 nickels, like these 5 nickels that I have at home, assuming I haven't spent them, these 5 nickels, if you count them up, there's 5 of them. Would anyone contest that and say that there's more than 5 or less than 5? Would it be wrong to say that I have 4.9 nickels? What if I had said I had 4.99 nickels? No, there's 5 nickels, right? We can count there's exactly 5 nickels. They might be slightly bigger or smaller, but if I go and take those to a cash register and try to buy anything that costs 25 cents, I can't imagine what that would be. They would say, okay, thank you for your 5 nickels, that's 25 cents. Here's your singular piece of bubble gum. If we counted up the number of students in the class, let's just say that it looks like all the seats are filled, so let's say there's 60 students in the class. Would anyone contest assuming that the number is correct, that there's 60 students in the class. No, there's exactly 60 students in the class. There's not 59.5 students in the class, because then somebody would have called 911 and I would probably, or whoever did it, would be under arrest. You can't have half of a student. We're all slightly different sizes. We would all count each of us as one person, one body, right? We are discrete. We're contained in a space, in a form, in a package. Countable whole number beings. However, if we were going to talk about this bar of gold, for gold and silver and other fine metals, usually they're described by a percentage or something that's like a percentage of how much gold or silver or whatever the precious metal is in that thing. So this gold bar, which I definitely have at home, it's not sitting in a museum somewhere where they mine gold. This 250 kilogram bar of gold, again, this is in my house, definitely not in a museum somewhere else in the world. This says it's 999.9 gold, and that's out of 1,000. So this is a bar of gold that's 99.99% gold. So it's almost entirely gold, but it would be wrong to say that it's 100% gold. There's probably a little bit of something else in there. But whoever made that bar of gold said, we can certify that out to this many number of digits, it's gold. We couldn't round that up and say it's 100% gold because it wouldn't be quite accurate. Generally, that's about as close as you'd ever want to get to 100%. Another example related to the gold, the global temperature on average has risen by 0.7 degrees Celsius since 1880. Based on analysis of records from thousands of temperature measuring stations around the world. So scientists have collected data from all these temperature measuring stations, all these data records going back to the 1800s. And they compiled all of them like for days and years and stuff. And this is how we get like, this is the hottest day on record for, August 8th of, all years. This is the hottest it's ever been on this day. It's because we have these temperature records. If we reported this differently, if we added zeros to the end of this, it doesn't convey the same information. And we probably don't have a good grasp for how that feels yet. But if we add a 0 to the end, 0.70 degrees Celsius, that would imply that we've measured out to the hundredths place for degrees Celsius. Most, like normal people, temperature measuring equipment doesn't go to the hundredths place. If we added another one going out to the thousandths place, that would probably be some pretty expensive temperature measuring equipment. And it's a little bit pointless for measuring the weather to go out to that level of precision. If we use the average, an example of an average that might be displayed by the computer with all of these decimal places, this implies that all of the temperature measuring stations and records went out to this many places, all the way out to wherever this 4 is, the millionth of a degree Celsius, which is just an absurd level of precision for just measuring the weather. So it's more accurate to say this 0.7. It's reasonable to assume that all of the temperature measuring stations around the world measured to 0.1 degrees Celsius, or 1 degree Celsius, depending on what sort of measuring equipment they had. And so the way that we keep track of the number of decimal places that we can include in our reported answers is with significant figures. Which we'll talk about on the next slide. When we're reporting measured quantities, like in a lab report, or a data table in a lab, we reflect the precision of our measurement, how small of a unit, how fine of a measurement we were able to make, by the number of digits. And the uncertainty is reported in our last digit. So in any measurement, the last number is a little plus or minus. So it could be a little bit higher, could be a little bit lower. We're just saying kind of like, yeah, it's about there. So this 0.7 could be 0.69, could be 0.71. There's a little bit of uncertainty about where that exactly is, but we can say for sure that it's about 0.7. Typically, we're going to have more decimal places. So for example, in this 45.872, we are absolutely sure about these first four numbers. We'll see some examples of this uncertainty when we're taking some measurements later in the slides. So we're completely sure that it's 45.87, and then the 2 is estimated, or it contains our uncertainty. So it could be 2.1, 1.9. Like if we were to measure it with better equipment, it might be that it's 1.9, could be that it's 2.1. There's a little bit of plus or minus with that last number. But we're absolutely sure about all of the other digits. When we are taking measurements, which we'll be doing next week, and I think we're doing measurements lab next week, when we're doing measurements, it's important that we write the correct number of numbers. So for example, if we're measuring the diameter of this nickel, we'd put our ruler up, we'd make sure that the 0 side is lined up with one edge of the nickel, and then we would look at where does the other end line up on our ruler. So if we're looking at this, it's in centimeters, we're definitely past the 2. Right? Nobody would contest that we're not past the 2. We're not to the 3. And then we've got subdivisions. And another nice thing about the metric system is that we're always going to have 10 subdivisions. So we've got this middle mark that's a little bit shorter or a little bit longer than the other subdivisions. That's our 5. And that's typical. So that would be our 0.5. Mark in between, so 2.5. And then all these other ones that are the same height are 0.1. So if we computer enhance and get in here, right, where we've got one subdivision, this would be our 2.1 mark. The next one would be our 2.2 mark, and these are again centimeters. Would anyone contest that we are not past 2.1? Would anyone say that we're not past 2.1? I would say we're definitely past 2.1. We're not quite to 2.2, right? And then we can estimate how far between the 0.1 and the 0.2 are we. Are we right at the 2.1? Are we about halfway? Are we a little further? Usually we would do this on a scale of, I say, 0 to 9. So from 0 to 9, how far past the 0.1 are we? Where does this line fall? Yeah, less than 0.5. So it might be 0.4, 0.3, 0.2. And that's the estimated part. So all of us, we can all agree about this 2.1. We can all agree it's past 2.1. And then we would visually estimate, break it down into tenths, how far past. We might come up with 2.12, 2.13, 2.14. 2.15 is too high. So there's a little bit of uncertainty. We would have to estimate that last extra digit. So whatever our smallest unit is, we want to make sure that we're estimating how far from that one unit to the next little marking. So this is where the estimation or the uncertainty comes in when we are taking the measurement. This is a balance that's measuring in kilograms. And this was one of the few pictures that I could find, because I did actually make these slides. This was one of the few pictures that I could find where somebody was standing on a scale and they didn't just have their bare feet out. And it was also free to use. I didn't feel like stepping on a scale and showing you all my weight. I also don't have an analog balance. So I found somebody, thank you to whoever put this up, and was wearing socks. Awesome. So this balance has markings of, this is our 115, our 120 is here. We've got a couple of marks in between. So these are 1 kilogram per smallest mark. or our smallest little tick or byte. And so we would look at, we're past the 115, we're past the 116, we're past the 117 because we can see the 117 mark. We are not to the 118. So the part that we can hopefully agree on is that we're at least 117 kilograms, or whoever this is, at least 117 kilograms. And then we would estimate how far past 117 are we. We're a little bit past, we're not quite to the halfway point. So we would just do our best. It might be that we see 0.2, 0.3, 0.4, kind of similar to the previous slide. So these would all be good measurements. As long as we included kilograms. Any questions about these measurements so far? Notice that those are 3 different numbers. The most important thing when we're taking measurements, these are called analog measurements. So analog measurements are where you read off, you figure out where the number is. So like an analog clock where you have to read the hands, like the one we have in the back of the class. You have to read off what time it is, or on this scale, what the mass is. You're not just given the numbers. Here's the number, right? Digital clocks just tell you, here's the time. Digital balances or scales tell you, here's the number. When we're doing analog, when we have to come up with the measurements, there's a little bit of plus or minus just because of how we're going to estimate. The most important part, what I will be looking for, especially on labs, is did you do the estimate? That's the most important thing. Also, if you take a measurement, assuming it's close to what it should have been and what I expect to see, I wouldn't know if you read it wrong. But I'll definitely know if you leave off the estimate. So you want to make sure that we're going one place past whatever our smallest unit is, and I think I've got that written out more explicitly coming up. This is a 4-beam balance. We'll be looking at 3-beam balances, I believe, in lab next week. So the way that a 4-beam balance works, these are kind of archaic at this point. You've got 4 beams. That's why it's called a 4-beam balance. And each of them is for different place values. So at the very back, we've got a slider that notches in to 0, 100, or if you look in the back here, 200. So that sets our hundredths place. And what we're looking for on here is, over on this right side, does this little lever thing hit the 0? If it hits the 0, if it's level, then that means the mass that we've got on these 4 balance arms is equal to the mass of, in this case, the most indestructible phone in all of humanity. And so we would move over our big slider, our 100-gram slider, 0, 100. Okay, it's not over at 100. We move to 200. The scale tips down. We've overshot it. So we move back to the 100. And then we repeat the same process with our tens place. So this one we've got at 30. And we would do the same thing with our ones place. This one's at a 0. I'll bring my 3-beam balance in at some point as well if you want to come play around with it in my office. And then the last one doesn't click in. It doesn't lock into a specific spot. So this is the one that free slides, and this is where we do our measurements. So our smallest measurements on our little balance arm at the front here, right, that's our 0.1. So then the tick marks our smallest tick / measurement size, or space between 2 ticks, is 0.01. So if we look at this, the balance beams, we've got 100 plus 30 plus 0, so 130, 0.5, and we're about at the 1. And then if we zoom into the image that I already zoomed into, to me it looks like we're right at that mark. So 0.51, and we're maybe right at it. So my estimate is that we, and by we I mean the slider, are exactly at 130.51. So my estimate is 0. We're not any further past the 0.51 mark that we've got there. So the estimate part sometimes will just be adding a 0, and it's important that you add that 0. This is like one of the big places where people forget or screw up with making their measurements is they forget to add the 0. Another thing that people will do is they try to add too many decimal places. And we'll see that. I'll show you an example of that once we work on this exercise. So let's say that we're staying in a cabin in the mountains during the winter and we want to figure out how much to bundle up before going outside. We've got an outdoor thermometer. So we look out and we see this thermometer and we obtain a reading, the one that we see there. We want to know what's the temperature so that we can report it to the rest of the people in the house. How much do we have to bundle up? So go ahead and give that a shot. Try and read off what that number is, and I will give you a little bit of time to do that. All right, we've had a little bit of time to look at our temperature, or whatever this says on it, our temperature meter outside. So we want to figure out what would be the scientifically reported value of this temperature. A little bit silly if we're just trying to figure out how much to bundle up, but it's fun context. So we've got our 0 mark. Moving to the left, we can see we've got -10. So we're somewhere in the negative numbers. We could count over from our 0. -1, -2, 3, 4, 5, -6, -7. And what would the next tick mark be? -8. We're not quite to the -8, right? Right. So we're between, we're definitely past -7 degrees Celsius, not past /2 -8 degrees Celsius. So we're somewhere between -7 and -8. Just as a note for the way that I write, this plus, but it's got the little connection thing on it, that means and. I picked that up in some class because an instructor was doing it. I was like, I like that, it saves time. So we're between -7 degrees Celsius and -8 degrees Celsius. We want to know how far past are we. So looking at, let's mark it out, looking at -7 degrees Celsius, -8 degrees Celsius. On a scale of 0 to 9, how far past the 7 are we? We're more than halfway, right? So it might be 7, 8, maybe 6. So any number of these would be good. 7, -7.6, 7, or 8, all in degrees Celsius. These would all be good measurements. Part of the reason that I have been framing it as we're between this number and this number is because we won't always have a scale that runs in the direction that we think it does. Sometimes instead of things counting up as they go up, they count down as they go up, or they count up as they go down. Question?
Do we add a 0 to this, like in this scenario?
We don't add a 0 to this. So what a 0 would mean if we added a 0 onto this. We've got singular units, units of 1. We can pretty reasonably estimate 10 divisions between those two marks. How many of you have the hubris to believe that you could measure accurately 100 measurements, 100 divisions between those two little marks? Probably no one can do that unless you're a very special kind of individual. I don't think we have any of you in this class. And so we can only measure tens. So that's why we just do one extra place over instead of 100. And that's where some of the issue comes in. Sometimes people will be like, oh, it's like, let's say it was right on the -20. I'd be like, oh, it's negative 20.00 because it's really, really right on it. Red flag. Too many decimal places. So we want to make sure that we're just doing one extra decimal place. That's typically what it's going to be, is just one extra decimal place. Or one extra place over. Any questions about the reading?
So whenever we're estimating, if it's the estimate, we never put a 0, right?
You can put a 0, only if it's right on one of the tick marks. If it's right on one of the tick marks, then it's whatever that tick is. So like if it was right on the 7, it would be 7.0, because we estimated that it was right on it. So sometimes a 0, but only if it's right on one of the marks, and only 1 0. Never 2 zeros, unless it's a 0 mark. Okay, now for the fun of significant figures. Before that, though, digital measurements, because I don't have it in my slides. Digital measurements, I don't have them in the slides because I think they're very easy. If we read the time off of a phone, like mine says 11:09, what time is it? 11:09. It's 11:09. That would be what we would report. If we go and read off a digital balance in the lab, we've got something on the scale, and if that something on the scale says 4.17 grams on the scale, what would we report? 4.17 grams. You just write down what it says. You don't round it. You don't add anything. You literally just copy it. If it's digital, yeah, then you just copy it down. Just whatever it says, that's what you write down. The nice thing about digital scales, digital measurements, is that they are including the uncertainty. They're including the little bit of plus or minus. They've already estimated for you, so you don't have to do any estimating. You don't have to do any guesswork. You read the number, you copy the number. That's all there is to it. So just copy the number. Whatever it is, copy it. If there's zeros at the end, write the zeros. If there's not zeros at the end, great. Doesn't really matter. Just write it down. I have to say this because I occasionally do get people that say, oh, I wanted to, well, I rounded it. Why did you round it? It told you what to write. So don't round it. Don't add anything extra. Just what you see is what you get. All right, significant figures or significant digits, as other instructors or other people might call them, or how we would figure out how many numbers to carry through for our final answer, like if we're doing multiplication or division or addition, subtraction. Because if you multiply two numbers, and there's some decimal point stuff, right? You plug it in your calculator, it's going to have a whole long string of numbers. We need to know how many of those do we keep. Where do we cut off our calculator and say, enough is enough? You've given me too many decimal places. So that's why we go into all this bother about significant figures. The other reason that we do significant figures is because if we wanted to do things the way that we would do them properly in a lab, we would do propagation of error. And propagation of error involves calculus. Calculus is not a prereq for this class, and I don't want to teach you calculus. We're going to do significant figures instead. It's a lot easier. So propagation of error is what you'll do if you go on and you do higher level science. You'll probably do propagation of error, but for now, we can live with significant figures. It's good enough. So our rules for significant figures. All non-zero digits are significant. There they are, all of our non-zero digits. Anything that's not a zero is always significant, no exceptions. The numbers that we're talking about here, we're assuming these are measurements that we made or something. So all non-zero digits are significant. Our 1, our 5, these two ones. Interior zeros, zeros between two non-zero numbers, are significant. So all of those underlined in red, those zeros, those are also significant. if we have trailing zeros are significant if there's a written decimal point. If we don't have a written decimal point, intrigue. So 5.10, that 0 is significant. 500.0, that trailing 0 is significant. But then all of the other ones are also significant because we've got a written decimal place. Questions so far? Yes?
Just to make sure for number 1, that 0 at the end is also significant then, right?
Yes, the interior 0 here would be significant. The trailing 0 here would also be significant. Other questions? All right, more rules. Here's the intrigue. Trailing 0 is before an implied, not written. Decimal point are ambiguous. They might be significant, they might not be significant. There's not a written decimal point, so we can't be sure. And so in this number 50,000 and in this number 10, we've got trailing zeros. There's not a written decimal point, so we don't know that they're significant. And so, for example, this 50,000, the 5 is definitely significant. So at a minimum, we've got one significant figure. 1, 2, 3, or all 4 of these zeros might be significant. So we could have anywhere between 1 and 5 significant figures for that number. The problem with writing down a number like 50,000 is that we might know how many significant figures it's supposed to have. We might know maybe it's 2 of those zeros are significant. Somebody else coming along later, based on the rules that we have for significant figures, wouldn't be able to figure out it's 2 significant figures. So generally in these cases, if we have trailing zeros and an implied decimal point, we're going to use scientific notation. It's part of why we learn scientific notation. So an example of this, 350 definitely has 2. Definitely 2 significant figures because the 3 and the 5 are non-zeros. And then we've got this ambiguous 0. Is it significant? Is it not significant? There's no written decimal point, so we can't be sure. So if it's got 2 significant figures, we would convert it to scientific notation. No trailing 0. 3.5 times 10 to the 2. Just 2 significant figures. For sig figs, we're always just looking at the decimal part. If we wrote a trailing 0 after a decimal point, what color did I use for that? Oh no, I used green. It's fine, nobody cares anyway. 3.50 times 10 to the 2. This has 3 significant figures because we've got a trailing 0, and look at that, our written decimal point. So this is one of the weird areas of significant figures. And then another one, I think this is our last significant figures rule, leading zeros are not significant. They're never significant. They only serve to show us where the decimal point is relative to our first significant number. So these zeros are not significant. And you know that they're not significant, even though you didn't know that you know that. If we were to convert these into scientific notation, for example, this 0.0153, we would move our decimal point to be after our first non-zero number. Our decimal part would be 1.53, not 0.001.53, right? That looks silly, looks weird. That's how you know that those leading zeros are not significant, right? You wouldn't write them there if you put them in scientific notation. And then times 10 we bumped our decimal place over 3 spots. It's a small number, so -3. 1.53 times 10 to the minus 3, if we put it in scientific notation. Questions about significant figures? So this is a process that you'll go through when you are given numbers, like on an exam, or from a digital measurement, or from analog measurements that you make. You'd count up how many significant figures does our measurement have. There are also, and this is sometimes confusing, exact numbers. So exact numbers we consider them to have unlimited significant figures. Exact counting of discrete objects, that was what I was talking about with like the nickels or the students in the class, where it's like, yeah, there's definitely 5 nickels. Yeah, there's definitely 60 people in the class. So things like nickels, people, dogs. Cats would also count. So those would be examples of discrete objects. You can't have a fraction of those things. Some integral numbers that are part of an equation, like numbers that are necessarily part of an equation, can also be exact. And some defined quantities. So some conversion factors. For example, inches and feet are related to each other. They're defined as 12 inches equals 1 foot. That's part of the definition. It's not like we rounded it to 12. They're based off of each other. So 12 inches in a foot. Not all conversion factors are defined quantities. This is my general rule of thumb. So like for conversion factors, no decimal part. So 12 inches in a foot, it's a whole number 12, not 12.1 or 12.0. So that would be exact, or we could assume that it's exact. 5,280 feet in a mile, 1,000 kilometers in a megameter. I meant to say 1,000 meters in a kilometer. So just as a note, all metric prefixes, conversions are exact. Prefix conversions. So anytime we're converting between those prefixes that we're going to come to know and love, those are all exact, so we don't consider the significant figures. Basically what it means, for the purposes of doing calculations, is we can ignore the significant figures. We just ignore that number. We only focus on the other things. All right, an exercise to wrap us up. An example, I guess. How many significant figures are in each of these numbers? So 5.87. How many significant figures does it have? 3. It's 3 because we've got 3 non-zero numbers. What about 0.031? It's 2. 2 significant figures. The non-zero numbers, the leading zeros, don't count. Those are not significant. For C, 52.90. How many?
4.
We've got 4 because we've got a trailing 0. So this 0 is a trailing 0 after a written decimal point, so it is significant. 00.2001. How many? Also 4. those leading zeros don't count. We've got our non-zero numbers and interior zeros, and I don't remember what colors I used for these. How about E, 500? At least one, possibly two, possibly three. So this one is ambiguous. So somewhere between 1 and 3 significant figures. We know that it's definitely 1 because we've got the 5, which is a non-zero number, but the zeros, we're not sure we would want to put that in scientific notation. How about 6 atoms? What if I said 6 humans? How many significant figures does that have? Just like Sheaves' power? Unlimited. So we've got infinite sig figs. Because they're discrete. Not like on the down low, but like contained, countable. Questions about any of those? Yes?
If we're given like 500, do we have to convert it into scientific notation?
So 500 here, if you got 500 as a measurement, wait. If you got 500 as a measurement, then you would have to put it in scientific notation to show how many decimal places it is. If it's 3, then another thing that you could do is write 500 and then the decimal point. It looks a little weird. You wouldn't add a 0 at the end. 500 with the period, that would be 3 significant. We've got a written decimal place. Other questions? Then we'll stop there for today.